Imagine a point in space where gravity is so strong, not even light can escape it. A place where time slows down and the very fabric of space and time curves in on itself. This is the mystery of the black hole, one of the most mind-bending predictions of Einstein's theory of general relativity. In this video, we will explore the first solution to Einstein's law of gravity, the wild conclusions one draws from such a solution, and the seemingly unexpected scenario from which this solution came. Today, we ask, what happens when you fall into a black hole? In the early 20th century, the world was on the cusp of a revolution in our understanding of the universe. And while Albert Einstein had just unveiled his theory of general relativity, one man in a remote corner of the world took these abstract equations and transformed them into something extraordinary. You see, in the midst of World War I, while serving on the front lines as a soldier, and while battling a terminal illness, Carl Schwarzschild, a German astronomer and physicist, did the unthinkable. He worked out a solution to one of the most difficult equations to solve, Einstein's equations of gravity. And what the Schwarzschild solution led to was a mathematical structure describing the formation of what later became known as a black hole, and the idea of something called an event horizon. To simplify the calculations of the gravitational field produced by a massive star, Schwarzschild used spherical coordinates and exploited the symmetry of the sphere. R represents the radial distance, theta the polar angle measured from the z-axis, and phi represents the azimuthal angle in the xy plane. The Euclidean metric for flat space yields the typical line element that calculus students are aware of. Now, if one is to work in spherical coordinates, we must have some transformation rules from spherical to Cartesian, which are given here in R3. And thus, along with calculating the differentials in each of the directions, and then substituting the values we have for those partial derivatives, one gets the following relations. dx can be given by this expression, dy by this expression, and dz by this expression. So our line element can be written as dr squared, r squared, d theta squared, and r squared sine squared theta d phi squared, which gives us the metric tensor components in spherical coordinates. Now, if we make the move to four-dimensional space-time, we have a time coordinate to incorporate, and then we have a metric signature to incorporate as well. Here in the four-dimensional space-time metric, we have here in spherical coordinates g mu nu given, and we assume c, the speed of light, equal to 1, with the metric signature of the time component being positive, the spatial components being negative, given individually here. So the line element for a flat Minkowski four-dimensional space-time in spherical coordinates is given as follows. One recalls from Einstein's law of gravity that in flat spacetime r mu nu equals 0, that is in the absence of matter or energy. So the line element for a static, spherically symmetrical spacetime incorporates functions which are only radially dependent. A and B are functions that give rise to the time and the radial components of the metric tensor. Now, if we take the Einstein tensor developed from the Bianchi relations, we require that its components be 0 as well, and therefore the time component, or the g00 component, be equal to 0, yields the function a equal to 1 minus 2m over r, where m is the integration constant that can be interpreted as the mass of the central object. The radial component br is given here as the inverse of that same term. Thus, we can write out the line element in this fashion. Thus, we get an expression that flattens out as we move further away from the mass, generating the gravitational field. Taking a deeper dive, static conditions mean that the metric tensor are independent of the time coordinate. It also means that the spacetime elements are also 0. Thus, spatial coordinates given by r, theta, and phi yield the general form of the line element written as ds squared equals this, which doesn't look much different from what we were talking about. And here, it is most convenient to allow the function c of r to be equal to 1. And then this in turn gives us an expression which we can write as this. Now you'll notice that the functions a and b are given by exponential functions. These exponential functions are due to the functions being solutions to differential equations of this particular form. Alright, so let's put this all together here. We thus get the time element to be e to the 2 nu, the radial element to be negative e to the 2 lambda, and then the radial components are considered as well, where the rest are 0 when mu and nu are not equal. It is from these components that we can then further calculate the Christoffel symbols, so we'll write those out explicitly here. Taking our time to write out each one of these components, but one would notice that many of the Christoffel symbols also vanish. Elements that have primes or denuding primes or differentiation with respect to the coordinate r. And thus from the Christoffel symbols one can then calculate the Ricci tensor components, and as follows we get the following expressions. We are getting these by substituting the Christoffel symbol values into the expression for the Ricci tensor. And all other components vanish. Now we have the Ricci tensor values, we can now use Einstein's law of gravitation to apply this, and what that means is letting the Ricci tensor components equal 0, thus getting the relationship here, and for large values of r, we must approximate space to be flat. Thus, we get lambda and nu to both approach 0 as r goes to infinity, and that follows that lambda and nu added together equals 0. And if our R22 component is 0, we get this expression, which we can write in a more compact form, revealing this as a solution, thus giving us the equation for our function a to be 1 minus 2m over r, where m is the constant of integration, again interpreted as the mass of the central object. This also makes the components r00 and r11, the time and the radial components of the Ricci tensor, to vanish. Thus we have the time component of the metric tensor here. And since the Newtonian approximation must hold for large values of r, we can compare this time component to the calculation we made in an earlier video of 1 plus 2 times v, where v is the potential of the gravity field that is produced. This tells us that the constant of integration m is just the mass of the central body, and under these conditions we get the complete solution to look as follows. This is what is known as the Schwarzschild solution, and it incorporates the Schwarzschild metric. It is the field equations that describe what's going on around a massive body like a star, or a consequence of these solutions, a black hole. So let's talk about some black holes, i.e. the consequence of the Schwarzschild metric. Here we'll write out the line element for the Schwarzschild solution, and we'll notice that this component here is the time component, and this component is the radial component. We'll, for the most part, ignore the angular parts, and we'll just focus on the time and radial components. We notice that these solutions become singular at r equals 2m, which is known as the Schwarzschild radius. It is the radius beyond which the mass begins to create something very interesting, because the time component will go to 0 as r goes to infinity, but the radial component goes to negative infinity. It blows up in the negative direction, as it is attractive. Thus we are talking about a singularity. So it seems that r equals 2m gives a minimum radius for the body of mass m. But a closer investigation of this situation will show that this is not actually so. One must consider a particle falling radially into the central body, and we'll let its velocity vector be given here by this expression. S is the proper time, and thus if we're moving in the radial direction, v2 and v3 will be equal to 0, and motion will be determined by the geodesic equation given here, or in the coordinate system form here. Doing a few calculations here for the velocity time component in reference to the proper time, this yields the value of the time component when the particle starts to fall. Doing a few calculations here and simplifying, this integrates to the following constant. Again, this is the value of the time component where the particle starts to fall into the central body. And thus we have this as a result, where the velocity vector has unit speed multiplied by the g00 or the time component, and using a value we got from an earlier video, we find this relation holds true. Thus, for a falling body, the acceleration is less than 0, the radial distance is decreasing, and we can write this expression for v prime. Now, taking the ratio of dt over dr, which is the time component over the radial component, we get this expression. And suppose the particle is close to the critical radius of 2m, thus there's a small variation in the distance between it and 2m. Then in this case, dt dr is given by this expression, which integrates to this. Thus, as r approaches 2m, t approaches infinity, the particle takes an infinite time to reach the critical radius, r equals 2m. To the outside observer, the particle is frozen in time. But now what if we're traveling along with the particle? As the observer's time scale is measured by ds. And ds dr is given by this differential equation, which we notice that as r approaches 2m tends to the value -1 over k. Thus the particle reaches r equals 2m after a lapse of finite proper time for the observer. So ds dr approaches -1 over k. What does this mean for the observer? Well, that's like asking the question, what happens inside? You see, we must examine what happens as we continue the Schwarzschild solution for values less than 2m of the radius. Once we have entered the event horizon, we must change our coordinate system from static to non-static coordinates. That means that we're going to make g mu nu vary with the time coordinate. Space-time begins to change inside the black hole. Now we'll keep our angular components unchanged. But instead of t for time and r for radius, we'll change to the new variables tau and rho, where tau is equal to t plus some radial function, and rho is equal to t plus another radial function. Differentiating these two equations with respect to the radius, we get a pair of differential equations. And from this we can write out that d tau squared minus 2m over r d rho squared gives us this expression, which we can simplify a little. And then eliminating f from the equations, we get this particular expression. You see, we're really only interested in the time and the radial component if we're keeping the angular components unchanged. If we choose f and g to satisfy these two conditions, then we get this expression, eliminating f from the equations. And now this is a differential equation which is going to be solved through integration. And we integrate this by letting r equal y squared, and r is going to be greater than 2m. 2m will let equal a squared, so therefore y is greater than a. And we get this pair of differential equations, which, well, this single differential equation, which we will in turn rewrite as this after we integrate it. And finally, using these conditions, we have the following. This gives us a radius with a component here, mu, and that leaves a line element in terms of our new variables rho and tau here, which shows that the critical values r equals 2m correspond to rho minus tau, which is equal to 4m over 3. In other words, in this particular representation, the singularity disappears. So the coordinate system makes a difference. We know that the Schwarzschild solution satisfies Einstein equations for r greater than 2m, and by analytic continuation, we can infer that the above metric holds for r less than or equal to 2m. It may continue to hold for r equals 0, or for rho minus tau equals 0, which means that rho equals tau. So where does the singularity come from? The singularity is a mathematical object, and it appears in our connection between two different coordinate systems, a new and an old. Thus, it is a problem in the representation of what we are trying to describe in a transition zone. Now, if we make a few modifications to Einstein's equations in the presence of matter, in other words, first we considered Einstein's equations in the absence of matter, leading to the Ricci tensor being equal to 0 and the Einstein tensor equaling 0 thus. And by contraction we got this value, so that when matter is present we have to replace r mu nu with a tensor of value, and thus the Einstein tensor is also not going to be equal to 0. We'll let it equal to y mu nu. So these two tensors are the result of there being the presence of matter. And we use the Bianchi relations, which encode the Einstein tensor, which requires this relation to be true for the covariant derivative. And for convenience, we'll bring in a constant of negative 8 pi. Thus, we have this relation holding true in the presence of matter. And these particular quantities represent density and flux of the energy and matter in question. Thus, we get a raw form of Einstein's equations for general relativity. I leave the rest up to the physicists to describe to you the nature of matter and energy. Well, hey, thanks for watching. I hope you liked this video. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one.